Welcome back to the deep dive. So, you gave us a mission that, on the surface, sounds deceptively simple.
Uh-huh.
Unpack the absolute fundamentals of computing.
Right. The very beginning.
Exactly.
Yeah.
We're talking about the invisible blueprint, the architectural foundation behind every single application, website, and every device you touch.
It's a great topic.
Our sources all confirm that if you really want to get computing logic, you need to master one foundational mechanism.
The IPOS cycle.
The IPOS cycle. Input, process, output, and storage. This is apparently the core operation of any computational system, from a giant supercomputer all the way down to the chip in your smart toothbrush.
And this is where we really need to jump past the textbook definition.
Okay.
What's truly critical here is understanding why this four-step loop even exists. It's not just a descriptive model. I mean, it's really an architectural solution
A solution to what?
to the fundamental problem of computing, managing the massive, and I mean massive, speed mismatch between the outside world and the processing unit itself.
Oh, that's a great way to frame it. It's not just a cycle, it's a traffic management system. It's designed to overcome latency.
Exactly.
Okay, so let's unpack this universal blueprint then. Step 1, input. What exactly qualifies as input in this context?
Input refers to any data, signals, or instructions that are fed into the system.
Right.
You can think of it as the senses of the computer. It has to receive information before it can possibly act on it.
So a mouse click? Or
A mouse click, digital packets from a network card, even environmental readings from a sensor, all input.
And it always comes from outside the core processor.
Crucially, yes. This input always originates from outside the central processing complex. Comes from a peripheral or some other external source.
Which transitions us right into the concept of I/O.
Input-output.
Yeah, input-output, which our sources all emphasize, is the communication lifeline. If the CPU is the brain, I/O is like the entire nervous system connecting it to the world.
That's a perfect analogy. I/O is fundamentally the communication link between the information processing system and, well, everything external to the CPU and its immediate memory.
And when we say external, we mean vastly slower.
Oh, orders of magnitude slower. A human can type, maybe 50 words per minute on a good day.
If that.
Right. Meanwhile, a modern CPU executes billions of instructions per second.
That gap is just staggering. So if the computer has to wait for me to, hunt and peck on a keyboard, doesn't that waste huge amounts of processing power? How does the architecture handle that?
That is the billion-dollar question that computer architecture solves.
Okay.
When we classify an I/O operation, we define it as any movement of information to or from that CPU memory complex. And to prevent the CPU from constantly polling or checking a slow device.
Like asking over and over again, did you press a key yet? Did you press a key?
Yes, exactly that. Instead of doing that, the system uses mechanisms like interrupts.
Interrupts. So the keyboard sends a kind of distress signal when the data is ready.
Pretty much, yeah. It allows for parallelism. The CPU can be off doing something else entirely, crunching numbers, running a background task.
Right.
And when that external device, say a network card, finally receives a packet, it generates an interrupt request. That pauses the CPU just for a moment to handle the new input data.
That makes so much more sense for efficiency.
It's everything.
I always pictured I/O as communication with things truly outside the box, like a monitor or a USB stick. But I remember the source material making a very specific point. It said reading data from a hard drive that's inside the machine is also absolutely classified as an I/O operation. Why is the hard drive external to the CPU complex?
That is a perfect architectural insight. It really gets to the core of it. The CPU, its registers, and its primary memory, the RAM, they all operate on one extremely fast speed tier.
Like a high-speed inner circle.
Exactly. A disk drive, even a really fast solid-state drive, operates orders of magnitude slower than that.
So it's still the outside world from the CPU's perspective.
Yeah, precisely. Because the data has to be moved from that slow storage controller into the fast primary memory for the CPU to access it, that movement itself is an I/O operation. It's moving information across that communication bridge.
Wow. Okay, that one nugget completely redefines the computer's internal map for me. The CPU is just sitting in its high-speed bubble and everything else is external.
And it has to manage all of it through these communication protocols.
Okay, so the data is in, the CPU has received its instructions. Now we're moving into phase 2, process. This is the engine room, right? The transformation center.
This is where the magic happens.
Walk us through what manipulating or transforming data actually means inside the core.
So this is the heart of computation. The process phase is where the CPU takes that raw input and executes the instructions that the software provides. It's the instruction cycle, just in constant motion.
Fetch, decode, execute.
You got it. The CPU first fetches the next instruction from memory. Then it has to decode that instruction to figure out what it needs to do.
Is it an addition, a comparison, something like that?
Exactly, a data move. And then finally, it executes the command, which often involves its arithmetic logic unit, the ALU.
So if the software is the recipe, the process phase is the chef, and the ALU is the kitchen tool doing the actual cutting and mixing.
That's a great way to put it.
Right.
And within that execution, the CPU uses these tiny amounts of extremely fast temporary storage. They're called registers.
Okay.
These registers hold the operands, the numbers being added, or the pieces of data being manipulated right there, next to the processing core. This makes sure data is moved as little as possible to maximize speed.
So without this, the input is just raw data.
Just raw data. The process converts it into meaning. If you input the coordinates for a point on a screen, the process phase runs a mathematical model to figure out what color that pixel should be based on the program's rules.
That detail really makes the process phase feel less like a black box and more like this carefully orchestrated sequence.
It is. It's incredibly fast, but very methodical.
So the transformation is complete. We have a result. That takes us to phase 3, output. We have to deliver this back to the user or to another system.
Correct. The result of the process phase is the output. But the key criterion for success here is that it has to be delivered in a usable or understandable form.
What do you mean?
Well, if the process phase calculates the number 4, the output phase has to convert that raw numerical data back into the shape of the character 4 and then display it on the monitor.
Ah, okay. So the output peripherals, like monitors or speakers, are basically I/O systems, but in reverse.
Exactly. They translate the electrical signals generated by the CPU into forms that we humans can actually perceive.
But wait a second. Printing a large document is often delayed, right? If the process of calculating the layout is done, why isn't the output instantaneous? If the CPU is so fast, why are we always waiting on the printer?
That's the I/O bottleneck showing up again, just on the output side this time.
Oh, of course.
Even though the CPU has finished its calculation in a flash, the output peripheral, the printer, is still incredibly slow in comparison. So the system uses a method called spooling or buffering.
A buffer.
Right. The CPU quickly dumps all the completed data into a temporary memory area, the buffer, and then it immediately moves on to the next task.
It doesn't wait.
It does not wait.
Yeah.
The printer then just reads from that buffer asynchronously. It just chugs along at its own slow pace while the CPU is already busy with totally different calculations.
So it's the ultimate delegation strategy. The CPU is basically saying, I'm done with the hard part, you handle the slow delivery.
That's it, exactly.
Input, process, output. We've defined the flow. But the name of the cycle includes a fourth piece, phase 4, storage. Why does a cycle that seems so driven by this quick, temporary transformation need a static element like storage?
Because storage is the system's indispensable memory bank. And it serves two really distinct but crucial functions. They're tied to two different tiers of speed. And the source material really captures this well. It notes that retention ranges from immediate retrieval to retention across several years.
So we aren't just talking about long-term files here.
No, not at all. We're talking about the entire memory hierarchy. First, you have primary storage.
Like RAM.
Things like cache and RAM. This is volatile storage, meaning the data is lost when you cut the power.
Right.
But it's exceptionally fast, and it is absolutely essential for the process phase. This is the system's working memory. It's what provides that immediate retrieval for the CPU.
And the second type.
Second, you have secondary storage. Yeah. So hard drives, SSDs, archival tapes, this is non-volatile. Keeps your data safe for years.
But slower.
Much slower. And it's accessed through those I/O operations we talked about earlier. But you need it to store programs and data permanently when the system is off.
So that distinction between volatile and non-volatile storage is really the key. RAM holds what we're actively using right now, and the hard drive holds what we might use later.
It's a trade-off. You get incredible speed, but it's temporary. Or you get permanence, but with a latency penalty.
And this dual function is vital to the cycle itself.
It is. Input data is often stored temporarily in primary storage before processing even begins. Then the resulting output is stored, maybe temporarily in RAM or permanently to the disk, so that it can then become the input for a later cycle.
The cycle feeds itself.
It has to.
Okay, so let's synthesize this whole loop for everyone listening. We start with input, which is managed by I/O protocols to deal with those speed bottlenecks.
Right.
The data then enters the system to be transformed by the process phase using the instruction cycle and the ALU.
Mm-hmm.
The resulting data is then translated into a usable format during the output phase, again managed asynchronously by I/O.
Yes.
And finally, storage ensures that the data and instructions are kept safe, both for immediate use in volatile memory and for long-term persistence in non-volatile memory.
That continuous intelligent loop is the universal mechanism. Every single computational task, from fetching a web page to balancing a spreadsheet, is just a rapid, constant iteration of that IPOS cycle.
Yeah.
It really shows that computing isn't just about raw speed. It's about efficient communication and coordination between all these vastly different components.
You know, what really stands out to me now is that the underlying design wasn't just about making things fast. It was about designing systems to handle the slowness of the physical world.
That's the secret.
So now you have the structural understanding of how any computer handles any task. You've really got the universal blueprint locked down. This has been a genuinely deep and rewarding dive into the core mechanics of computation. So thank you for asking us to look past the surface definitions and into the architectural heart of it all.
My pleasure. And here's a final provocative thought for you to consider, building on this idea of IPOS being a universal operation.
Okay, let's hear it.
If the IPOS cycle is the fundamental structure for any computing system, does this framework also apply to non-digital systems that, fundamentally deal with information flow?
Like what?
Think about biological processes. They take sensory input, process it through the nervous system, generate hormonal or physical output, and store information in memory. It raises a really important question about fundamental information flow and decision-making, whether the processor is made of silicon or carbon.